Hi, everybody. Okay, can you hear me? So seems to work, the mic. All right, so thank you, Paul, for the introduction. And also thank you to Helen and Nick and Clemens for inviting me here. It's really nice. And so my presentation is about AlphaFold and its impact on streamlining structure solution. Here's a little outline of this talk. So first I want to remind a few properties of AlphaFold predictions. Then I want to go through using predicted models for molecular replacement. Then I want to discuss the new idea of iterating prediction and model building. And finally, I want to list some limitations that we face when we use predicted models. So let's start with that little reminder of some properties of AlphaFold predictions. So now starting from the sequence and a multiple sequence alignment, we can get quite accurate 3D predictions of proteins. And so one of the great strengths of AlphaFold is that it's capable to assess its own accuracy. So each 3D prediction comes with 2 confidence measures. And these are the following. So the first one is the so-called PLDDT, that stands for Predicted Local Distance Difference Test. And so this value identifies where errors are more likely in the predicted model. And it's a per residue value. So each residue has one number. And it scales from 0 to 100. And if the PLDDT is larger than 90, then it said this residue has been predicted with high accuracy. So Tom Terwilliger did a systematic study where he compared some predicted models and some experimental SART structures, and he came up with this handy chart. And this shows what to expect from AlphaFold models depending on the prediction confidence. So here in the leftmost column, you have the confidence value, the PLDDT, so larger than 90, 80 to 90, 70 to 80, and then less than 70. And here we have the median prediction error and the percentage of residues with errors over 2 angstrom. So if we are in this high accuracy, high PLDDT regime, then the median prediction error is 0.6 angstrom. And we have about 10% of residues with over 2 angstrom error. However, if we have less than 70 for the PLDDT, the median prediction error is much larger, 3.5 angstrom. And we have almost 80% of residues that have an error over 2 angstrom. So here's a real-world case. This is an AlphaFold prediction of an RNA helicase. The residues are colored by the PLDDT. So blue is PLDDT larger than 90, green if it's between 80 and 90. So here we see that this structure has been predicted with quite high confidence. And here we see from the chart before to what errors that translates. So this is one of the confidence measures, but the second confidence measure provided with each AlphaFold prediction is the predicted aligned error. So this is a matrix, and the values in this matrix essentially inform us about the certainty of the relative position between 2 residues. So we can learn something about relative domain positions. So let's look at the PAE plot. So it's very handy to look at this in a graph. So let's look at the PAE plot for our RNA helicase example. It looks like this here in the lower left. On the x-axis, you have residue I going for the full length of the sequence. And on the y-axis, residue J. So let's focus on one residue. Let's say residue number 100. The dark blue regions in this plot mean that the uncertainty in the relative positions is less than 5 angstrom. So let's go to 100. So if we go here from 0 to 100, from 0 to about 220, all the uncertainty is quite low. However, for this same residue, all the residues here from 220 to the C terminal, the relative position is less certain. So, and the same goes for all the residues in this block here. So we see these characteristics squares on this plot, and they inform us if there are some domains within the relative positions of the residues are quite certain. And if these squares here are separated, then we can learn that they're different domains, and we don't know exactly how they are oriented. So in this particular case, we can see that there are maybe two domains. We can also visually see them. And if we want to use this model for other purposes, such as molecular replacement or for docking, then it's maybe a good idea to cut this prediction into two different domains and use them separately. So to summarize, these AlphaFold predictions are really great hypotheses, and they can be really awesome. So here in the left, we see a superposition of the experimental density map and the AlphaFold prediction in pink. And you can see that up to the side chain orientations, it really fits very well. But that's not always the case. Sometimes they can be wrong. So again, here we have superposition of the experimental density and the prediction, and it doesn't correspond at all. And here is a case where there's some distortion. So you can see that here's some helical shape of the density, and we recognize that the prediction does also form a helix, but it's kind of distorted. It's not quite in the density, but it has similar shape. And so it's it's good to realize that for all these three examples, the PLDDT was high, so larger than 90. So even by interpreting these confidence measures, we would not necessarily know that in advance if parts of the structure are wrong or distorted. So how can we use these predictions? So the obvious way is to incorporate them into the conventional structure determination workflow. So here's what I mean by that. So here we have the different steps for the structure determination process for crystallography and cryo-EM. It's a bit simplified, so I really have the main steps listed. So for example, in crystallography, we start with data quality assessment. We solve the phase problem by molecular replacement or by experimental phasing. Then typically the models they're quite preliminary, so we need some model rebuilding. That's mostly done automatically. And once we have a suitable model, we can go to the cycle of refinement, validation, and interactive model building. In cryo-EM, basically, it follows the same procedure, except that we don't need to solve the phase problem, but we can do docking instead of molecular replacement. So when we want to use predictions, the obvious way is to use predicted models for molecular replacement in crystallography or for docking in cryo-EM. So let's look at the example of molecular replacement. So as we all know, molecular replacement, the idea is to solve the unknown crystal structure of a molecule using a related known molecular model. So in the past, this was typically a homolog structure. So unknown structure here is a cat. The known model is a cat that looks kind of similar, but if we look at the details, it's not quite the same. Now we can use predicted models. So the cat looks now much more closely, but as we have seen, there's some areas or some regions in this predicted model where we can have distortions. Look at the head, that's a little bit different. And there can be incorrect domain orientations. So the tail here is exactly the same, but it's differently oriented in the predicted model. So if we want to use predicted models for molecular replacement, we have to process them. And so that involves removing low PLDDT regions, split the model into domains if it's necessary, and convert the PLDDT values to B factors. So I want to walk you through one example. So that's an example from Randy Reed for phaser software. So it's a protein called POM-GNT2. It's a crystal structure that has been determined at 2.1 angstrom resolution. And here's a little cartoon representation how it looks like, how the deposited structure looks like. So let's do as if we don't know how the answer looks like. So let's take the sequence and get a prediction. So the full length sequence of this protein gives this prediction here. Looks kind of like protein. We see some helices, some sheets. Orientation of the domains seem a little bit odd. So we will have to look at the PAE plot to see if that makes sense. So first of all, let's color by PLDDT. Blue is good, red is bad. We don't see any red. We just see a little bit of yellow and orange here and there, especially between these regions here. And then let's look at the PAE plot. Here in the lower right, we can see here 3 squares. Little square in the upper left, that's this anchor helix. Big square in the middle, that's this big domain. And then this smaller square in the lower right, that's this smaller domain here. So according to the PLDDT and the PAE plot, we will now process this model. So we'll remove these residues that have low PLDDT and then split into domains. So then our model looks like that. Then we have to be careful if our construct that we used for crystallization, if it's the full-length protein or not. In this particular case, it isn't. So this anchor helix has not been included in the construct, so we don't need it if we want to do molecular replacement. So this is the processed AlphaFold model. And if we do molecular replacement and then compare it to the deposited structure, we see that they correspond very well to each other. So here is in green deposited structure, in orange is the molecular replacement solution. Now, just out of curiosity, I also ran a molecular replacement search where I used the 2 domains. I didn't cut them apart. And let's see what happens. So I still got a molecular replacement solution. And so this big domain, when I superpose this to our previous MR solution, they coincide very well, but you see that the smaller domain is shifted. So here's this beta sheet with the 3 strands. And you can see that the sheet is shifted by basically 1 strand to the bottom in the, if we use the AlphaFold model without being split into domains. So this model can be maybe used, but before we go to refinement here, we would need some serious model rebuilding in order to move to the next step. So it's really, in many cases, very useful to split a model into domains. So here's a little outlook for predicted models and molecular replacement. I'm sure many of you have seen examples where a predicted model was used, either yourself or in papers or maybe some collaborators. And Claudia Milan has shown that almost all crystal structure targets in CASP14 could have been solved by using MR. In Tom Terwilliger's study, he showed that 90% of 215 SART structures could have been solved with molecular replacement. I just went to the Lunchtime Bites presentation about molecular replacement, and I think there was a similar number that more than 90% of 400 SART structures also could have been solved with molecular replacement. So there will be less need for experimental phasing in the future, although it's still a method we need to know. And again, it's necessary to process the predicted models before we can move on to molecular replacement. Now I want to go to the other way, to a new approach that involves iterating, prediction, and model building. So here again is the simplified steps of the structure solution process. And you can see that here we have now 2 iterative steps. So not only refinement and validation, where we go round and round, but also we have model prediction and model rebuilding that we do several times. And I want to show you an example why this might be useful. So this time it's a cryo-EM structure that I use as an example. It's 7MJS. The resolution of the cryo-EM reconstruction is about 3 angstrom. Here on the left, you see the full-length model that has been deposited. It has 3 chains, X in red, L in blue, and H in green. And I want to focus on this chain H here. Now there's a loop that interacts with other chains, and that loop has not been predicted correctly by AlphaFold. So let's see how that looks like. So here from the sequence, we make an AlphaFold prediction, and then we get this structure here. Looks kind of like protein. Again, we have some better sheets here. This loop looks indeed a little bit weird, right? We have this wobbly trace of the main chain. So let's color this by PLDDT. And this looks like this. So the core of this predicted protein model has good PLDDT, so it's blue. And here we have orange and yellow, so that PLDDT is not as good. So now if we want to use this model for docking, let's remove all the low PLDDT residues. So we end up with this magenta structure. And then let's put this into the cryo-EM reconstruction like this. And out of curiosity, let's see where that loop, that floppy loop with low PLDDT, where that is. That is around here. And indeed, it does not fit into any of the density of this map. So it looks much more likely that you can see in the background here, there's a stretch of density, now shown in blue, where this loop could be actually located. So if we start now to rebuild our docked and trimmed model, we get this structure here. So here we have that loop that has been rebuilt, and it fits quite nicely into that density. And now, instead of moving on to refinement and validation, we will just do another round of model prediction. So this time, we will use this sequence as input, and we will use as template that rebuilt structure that has the good loop. And what comes out of this round of AlphaFold is a new prediction where the loop is now better than in our initial prediction. We end up with the same good loop. So here's a superposition of the first prediction where we just used the sequence in violet. So you can see here that bad loop pointing to the right. And in green is the prediction where we use the sequence and the rebuilt model as a template. So this will end up with a good loop. If we iterate this several times, then we will end up with this blue model. That's the final iterative predicted and rebuilt model. And in yellow, we have the deposited model. So the main chain corresponds very well. And here we have also now the side chains. So there's some side chains that still need some tender loving care. Let's see here, for example, the side chain point in opposite directions. But this is a very good starting point now for refinement and interactive model building. So by this iterative procedure, we can get as much as possible automatically. So here's the strategy for structure determination in the AlphaFold era. First step is to predict your structure, and then we can design our experiment accordingly. So we can choose the experimental approach. We can think about trimming at domain boundaries for the crystallization construct. And then we can solve the structure. So in cryo-EM, we can apply docking. In X-ray crystallography, we can use molecular replacement or experimental phasing. Then we can update our prediction. So we run AlphaFold again with the best model as a template. And then we can improve the structure. So we use the new prediction as a hypothesis, and we can rebuild parts where this prediction does not fit into the experimental density. And we iterate these step 3 and 4 several times until we converge to a model that doesn't change much more, and then we move on to refinement and interactive model building. So now I want to list a few limitations. So I grouped them a little bit by category. So first, it concerns the models themselves. And so as we know, RNA and DNA are not as accurate yet as for proteins, although there's some research in that area. And as we have seen in these examples, there are some high PLDDT regions are not necessarily correct. So we cannot blindly trust this PLDDT as saying this is the correct configuration of the protein. These AI models know almost nothing about physics and chemistry, and they generate only a single structure and no alternative conformations. So this has been brought up in the discussion yesterday, that we only get one single conformation, but we all know that protein conformations can be influenced by pH, temperature, the presence of ions, ligands, and if they interact with other proteins. Some limitations might be due to some procedures. So for example, MR procedures were optimized for homolog models. So maybe certain things need to be tweaked now to work also as well for predicted models. So again, these predicted models don't have conformational variability. So we cannot use that as guiding if certain parts are expected to move more. And maybe certain parameters were calibrated for homologs. And some limitations are for validation or future training. So one question is, are we actually able to distinguish predicted models from experimental model? So imagine someone just gives you a random PDB file. Would you be able to tell this is a predicted model or is this an experimental structure? And also one thing to realize is that templates that are AlphaFold models. So if we would do an AlphaFold prediction and we use a sequence and a template, if the template itself is an AlphaFold model, then the new prediction can have greatly inflated confidence. So you cannot necessarily trust these PLDDT values. And also, maybe I'm a pessimist, but I can also imagine these two scenarios here, maybe some more. Imagine you have a very low resolution cryo-EM map, and you dock a predicted model into that map, and this is not further refined. And maybe this ends up in the PDB. Is this then an experimental structure, or is this still a predicted model? And a little bit another case, maybe 4 to 5 angstrom map. Again, you use a predicted model to dock it into that map. And let's say you're only interested in a ligand binding or in an active site. So maybe this part is well refined. You carefully check if side chain orientations correspond to density, but maybe other parts of the protein are a bit more neglected because you have maybe 1,500 residues you don't want to look by one. And because these predicted models typically have very good geometry that are not flagged as outliers as such. And so again, maybe this ends up in the PDB, and is this then really an experimental structure or more hybrid? And so these are the limitations, and I just here have 5 more minutes, so perfect, because here's the summary. So AlphaFold models are great hypotheses, so it's really exciting that we can use these to solve our structures. They can be used for molecular replacement and for docking in cryo-EM. It's important to interpret the confidence measures that come with these predicted models. Iterating prediction and model building can lead to improved models. And I think as a user and also methods developers, we have to be aware of the limitations that come with these models. So this is all I wanted to tell you about streamlining structure solution. So as Paul mentioned, I work in the Phoenix group, which is a collaboration between many different people. So all of this work I presented here, I'm basically just the presenter. So most of it has been done by other people. So I just want to acknowledge everyone in Lawrence Berkeley Lab, Tom Terwilliger at the New Mexico Consortium, Randy Weed and Early McCoy, and Rob, who was a prior member, is sitting somewhere here. So from the Cambridge group. And then we have Jane and Dave Richardson at Duke University. And finally, thank you for your attention. So no bubble gun for me, it looks like.
Got any
I'm
questions?
a bit
Fire it if you want. I've got a question from the Slack. Are there common features or characteristics of structures that still fail MR using AlphaFold models?
I think one thing that was mentioned in, I don't remember if it's Claudia's or Early's paper, is that while AlphaFold, they still can predict helices very well, but there's the kinks or some subtleties that are not that great. So if a structure has lots of long helices, that might be something that's, even let's say PLDDT is very high, that might be a little bit disturbing for molecular replacement. There's one.
Is there a button on the bottom that's...
Robert from Aztec now. Yeah, so confidence measures.
without sounding flippant, maybe there should be a confidence measure of the confidence measures, such as the depth of the MSA, or how many iterations AlphaFold has been using. If it's not the default, maybe something the community could ask the developers of AlphaFold or OpenFold to provide something as a guidance for confidence measures, how much we can trust them.
Oh, so you want the how confident they are about the confidence measures?
Yeah, I mean, because if they're overconfident but wrong, then that's not helpful.
Yeah, I don't know if there's anything that they have in mind to bring up for that, but it would be great.
Hi, Peter Smythe from the European Expo. What does AlphaFold predictions do about potential partial occupancy or multiple conformers? Can it predict those? And does that affect how well it works as an MR model?
Okay, so I really have a little bit trouble understanding, so I'm just making sure I understand correctly. So about multiple...
Can AlphaFold predict multiple conformations, and does predicting or not predicting that affect the outcome of a molecular replacement using an AlphaFold model?
Okay, yeah, I think it can predict several structures, but most of them are very similar. So you don't get this conformational variability that you would get if you used homolog search. If these structures are all so similar, well, then molecular replacement search will not make much difference.
Great. I think we'll have to move on. I think we'll have to move on, but can we thank Dorothee again?